Okay. From ICID Central Office, I welcome all the participants of this webinar. I welcome all the speakers and panelists who will be delivering the presentation and then participating in the panel discussion. So today's webinar is on the tsunami tidal wave production in Japanese case. And just to give a background, Japan is a mainly rice paddy cultivation is the main measure of agriculture production in Japan, and the settlements are mainly in the river deltas and low-lying areas. 30% of the population lives in coastal area, and that out of the total area, agricultural land, 13% of the total agricultural land in Japan is distributed in lowland areas at elevation of 10 meters or less, which is affected by the tsunami and other coastal phenomena. And elevation, the low elevation areas around coastal area in Japan are believed to be very, very important from the agriculture point of view. And then on the other hand, Japan is a country that is frequently experiencing natural disasters such as typhoons, storm surges, and earthquakes. And serious damages on coastal areas caused by these events are often occurred, and countermeasures deal with such disasters, which are necessary for dealing with such disasters. The most devastating damage in recent years was the huge tsunami, which was caused by the Great East Japan earthquake of March 11, 2011. The magnitude of earthquake was at the level of 9 on Richter scale, which is the fourth largest earthquake worldwide. And then this earthquake caused tsunami waves, which are more than 30 meters in height. The agriculture sector was severely affected by the destruction of coastal dikes and facilities and the salinization of farmland and groundwater for using agriculture water. And the total damage was estimated as about 700 billion yen or $5.2 billion. The Institute of Rural Engineering, NARO, Japan, to which speakers of this seminar belong, has had professionals of various fields around rural engineering who visited the damaged site from immediately after the earthquake and conducted the on-site surveys and provided advice based on their knowledge and experience. This webinar will present information on the condition of coastal areas in Japan and past disasters, particularly the Great East Japan earthquake and subsequent coastal facility preservation effects. And also, this webinar will introduce the research conducted by the NARO on recovery situation from tsunami-induced groundwater salinization for restart of agriculture groundwater use. The technique related to the estimating of ground hydraulic conductivity is necessary for groundwater resource development in coastal area by using tidal response of on-site groundwater level observation data which will be presented during this webinar. The webinar speaker webinar will be delivered by Dr. Hiroki Minakawa, Japan, who is a principal researcher working in watershed management group in the Institute of Rural Engineering, National Agriculture for Food Research Organization, NARO, Japan. So now I request Professor Dr. Ragarava, President of ICID, to give his remarks on this webinar. Dr. Raghav.
Thank you very much, Harish. Good morning, everyone, and I'm really quite happy to see this working group of the SDTA organizing such a seminar on important issue. I came across that word tsunami. I didn't realize actually it is a Japanese name. It is a word actually coming from harbor wave. It was really something that apparently relevant very much to Japanese environment. However, I really remember very well what happened in 2004 when the tsunami came and was a devastating effect that killed about 230,000 people in 14 countries bordering the Indian Ocean. But the 2011 also tsunami in Japan also sent us a message that we should really pay attention to that sort of phenomena. However, actually, that it's not only to Indian Ocean where we see tsunamis. They are also they appear also in Europe, and they appear in the Mediterranean region. For example, in the year 365, there was an earthquake in Crete that actually affected all the Mediterranean countries, including the Nile Delta and Alexandria. And in Europe, we have seen in 1755 also Lisbon earthquake that also caused tsunami. That followed by 1783, another Caribbean earthquake and tsunamis. And in 1908, was also another tsunami in Sicily and Calabria. So it is really happening not only in the Indian or Pacific Ocean, but it looks like it is worldwide. And it is very difficult to actually to have a quite good warning and prediction of the tsunamis, and a lot of course scientists are trying their best to get pressure sensors and to predict the earthquakes and predict tsunamis, but it is really very difficult. And a lot of people, they started to use models nowadays also to try to predict the change in the pressure. I have been asked in 2010 by the Ministry of Agriculture and Fisheries here in the UK to look at the effect of sea rise and seawater inundation on the lowland coastal sites. And I've been looking at the impact of the inundation on natural vegetations, water and livestock and all the natural resources. And I'll leave that maybe to another seminar for me to talk about. However, it is very important issues. And I see we have excellent speakers today to listen to and to learn from. And I will leave you with the speakers, and I will enjoy with you a good deal of knowledge today about this phenomena. Thank you very much.
Thank you, Professor Dr. Raga, President ICID, for giving his remarks. Now I request Professor Kao, working chair of the working group SDTA, to give his address. Professor Kao
is muted.
Yeah, please unmute yourself, Professor Kao.
Okay. Now it's okay.
Yeah, that was okay.
Okay. I say good evening in Taiwan. Yeah. And first of all, welcome and greetings to all members who participate in the webinar on topic of tsunami and the tidal wave prediction in Japan case held by ICID today. And sincerely thanks Dr. Hiroki Minakawa for carefully planning and arranging this webinar. Dr. Hiroki is a member of working group of STTA and the principal researchers of the National Agriculture and Food Research Organizations in Japan. And at the same time, I would like to also thanks Dr. Yoshimoto and Dr. Katsushi. They are accepted the invitation for sharing their knowledge and experience. I read the news report on February 14th this year. The UN News headline reports a sea level rise post unthinkable. They are emphasizing unthinkable risk for the planets. The Security Council hears. In this news report, the UN Secretary General Antonio Guterres warning that in the coming decades, lowland community and entire countries could disappear forever and we would see ever fierce competition for freshwater, land, and other resources. Mr. Guterres warning the Security Council that under any temperature rising scenario, countries from Bangladesh to China, India, and the Netherlands will all be at risk. Mega city on every country, every containers will face serious impact, including glass, Lagos, Bangkok, Mumbai, Shanghai, London, Buenos Aires, and New York. The danger is especially actually from some 900 million people living in coastal zones and low elevations. 1 out of every 10 people on Earth, as we know. However, the tidal area along the ocean coastal line is located in the land and the sea interaction area. That is, normally, the ocean dynamics and the force such as ocean tidals, wave, and the currents, as well as the hydrodynamics interaction of the land water discharge into the sea along the river and the estuaries, as usual. In addition, the sea level rising due to the climate change and the land subsidence due to the exploitations of underground resources such as groundwater, maybe the petroleum and the natural gas and so on, have further aggravated to the potential crisis of coastal disaster. Today's we attend the webinar. The name the title is Tsunami and the tidal wave protection in Japan case. Japanese case is another type of coastal disaster. It is I think it's also one of main disaster of coastal area caused by a huge tsunami force and the ocean dynamics directly hit the coast caused by an earthquake in the sea floor. The tsunami may not only will be destroy the seawater and the coastal infrastructure, but also the huge amount of seawater run up to the land, and will flood the lowland and the coast soil salination and the infiltration of groundwater. How to rebuild it and the restore after the tsunami disaster. We're looking forward to sharing knowledge and the technology experience with us through the invited these 3 distinguished professors, research from the National Agriculture and the Food Research Organization of Japan. Welcome you. Thank you.
Thank you, Professor Kao, for your welcome address and giving background. Now we invite Dr. Minakawa to give his presentation on tsunami tidal wave production in Japanese case. Dr. Minakawa.
Okay. Okay. I think the resolution is not properly setted. We can't see the full screen. Can you reset the resolution, please? It's going out of the screen.
या अपने तरफ से प्रेजेंटर मोड कर लो
Sound करने से No, it's okay, perfect.
Okay. Let me start my presentation. Good evening. I'm Hiroki Minakawa from Japan. So my presentation is about tsunami tidal wave protection in Japanese case, especially using research information of our institute. Okay. And Japan is one of the island country, so total area is 380,000 square kilometers, and length of coastal line is approximately about 35,000 kilometers. So long. In coastal area, most of lowland area at elevation of under 10 meters or less is located. And the low area occupies about 6% of land. And however, about 30% of the population is living in the area, so it is important to protect them from disaster. Furthermore, about 13% of farmland is located in the low area, so that coastal area is also important for agriculture. And a coastal protection zone means a coastal area where must be protected from damage caused by tsunamis, storm surges, waves, etc. To preserve the land. Coastal line is needed of protection is 13,700 kilometers. It's about 40% of all of coastal lines in Japan. And if there are coastal protection facilities developed by land improvement projects from agricultural section, it's called farmland coast. Farmland coast means a coastal area with farmland located behind there. Farmland coast under the jurisdiction of MAFF is almost 20% of the coastal protection zone. And now, approximately 86,000 hectares of farmland is behind the coastal area. And in Japan, and 6% of there is reclaimed land developed by land improvement project with much social capital. The farmland is high productivity and highly profitable vegetables are grown. But there is a vulnerable to floods because of low elevation. And Japan is one of the countries where natural disasters occur frequently. And this is a little bit old data, but total damage cost associated with natural disaster in Japan was occupied about 16% of the cost of all over the world. This is in case of compare with 1972 to 2001. But and coastal area is vulnerable to natural water hazard like tsunamis, storm surges, and heavy rains. In recent years, tsunami related to huge earthquake has caused the biggest damage to coastal area of Japan. So, the East Japan earthquake occurred on March 11 in 2011, and the epicenter was in the Pacific Ocean near the Tohoku region of Japan. And it was the largest earthquake observed in Japan, and the magnitude was about 9. And it was the fourth largest earthquake event in the world since 20th centuries. And after the earthquake, a huge tsunami occurred, and it was struck in northeast region of Japan, like these pictures. And the land height had reached over 40 meters in maximum. And coastal facilities were destroyed by tsunamis, and farmland near sea area were inundated by seawater. And after the earthquake, liquefaction also occurred, and subsidence was a problem. But in present, it was raised again and almost returned to normal elevation. And normally, the design standard of facility construction has been established. Facilities must resist the event under the design standard scale and construct coastal protection facilities also has a standard. Before the tsunami in 2011, observed the highest record of tidal level was used for the design standard. It was corresponded with occurrence probability of once in 100 to yes. We call this standard level 1. After the tsunami in 2011, countermeasures for level 2 disaster was discussed. Criteria of level 2 disaster is the event with more than 1,000 years return period. So, and on the level 2 disaster, it might be impossible to prevent damage completely. So, integrated countermeasures is needed, so that the concept of disaster mitigation is important, and coastal flood is acceptable in level 2 disaster, which exceeds design standard scale. However, we have to minimize social damage even if the level 2 disaster occurred. And our institute, NARO, has sent many researchers to the damaged area immediately after the earthquake. And we contributed to restoration and reconstruction of the damaged area through investigation and studies. Today, I'll introduce one of the examples of our proposal to mitigate tsunami damage around the coastal area. The concept is to structure a tenacious rural area in coastal zones. The disaster prevention farmland realizes the concept. This is a concept of the disaster prevention farmland. It is multiple protection of residence area by using dikes and farmland. Under the concept, at first, living place moved to higher elevation area, and we readjust large farmland along the coast. And in the case of tsunami or storm surge, exceeds the planned dike height. Flooding on farmland are allowed. Some roads constructed parallel to the sea line. They work as second and third dike in emergency situation. And energy of water would be decreased by resistance of these facilities. And the proposal was based on the idea using not only a line of seawalls, but also an area surface of farmland to reduce tsunami power and protect residence area. And this is examples of case study on coastal area design in damaged area. Upper figure shows situation before tsunami, and there was a mix of agricultural land, agricultural and residential area. And below one is a new image. And based on disaster prevention concept, resident area moved to upland area. And location of farmland and railway were reconsidered. And at the same time, of considering concept, the method to estimate effect is required. So our institute addressed this subject by field investigation and numerical simulation and hydraulic model experiment. For example, by using numerical simulation method, tsunami run-up height with coastal area situation before disaster was reproduced. These results were used to estimate effect of countermeasures. So this is example of consider recovery plan in damaged area actually. First, the local government around damaged area had to develop a coastal dike with about 14-meter height. The 40-meter is very high and maybe safety, but there is a little bit problem that the landscape around coastal area will change dramatically. So then we compare the local government's plan, and in case of developed disaster prevention farmland with 77-meter height dike by using a numerical simulation method. So this and figure shows the result of inundation calculation, and P1 to P3 shows a checkpoint of calculation. And this figure shows result of inundation both plans were effective in reduction peaks compared to situation before the tsunami occurred. And you can see both of the peaks of the inundation depths are estimated almost same. The result indicated that these two restoration plans provided almost equally function. And however, focusing on the tsunami arrival time, so peak arrival time delayed about 90 seconds in our suggestion compared with the local government plan. So this is one of the effects to disaster prevention farmland. And after the verification, so these results were explained to residents in the tsunami affected areas. And we assist a dialogue communication for decide the rural reconstruction between inhabitants. After through this process, the representative of the rural people asked to employ the concept of the disaster prevention farmland for their revival plan. Thus, the research result and local coordination contributed to the creation of a plan for recovery from the disaster. And this picture shows the current situation of the area. In 2017, new coastal dike was completed, and big disaster had not occurred after 2011. And there is another problem. So related to agriculture around coastal area. To reuse farmland, salt removal was needed. So normally, ponding of farmland with rainfall and irrigation water were used for leaching of salt content from soil. And salt was moved downward with infiltration of ponding water, and also discharged with surface water drainage. And survey of salt concentration in water is very important to judge the water is suitable for agricultural water or not. So next speaker will present information related to this issue. And in coastal area, many types of disaster will occur in addition to tsunami. So nowadays, climate change is one of the topics of consider. So countermeasures to flood due to the increasing heavy rains or storm surges with big typhoon will be required. For sustainable development of tidal area, it is necessary to cope with various disasters by using various ideas and tools. So on this presentation, I introduced the proposal from our institute focusing on damage mitigation of tsunami disaster. And there is a limit to the capacity of facilities, and disaster that bound capacity of facilities will be occur someday. So it is important that effort to save lives and effort to minimize social economic damage and speed up recovery and reconstruction in the event of a disaster are important in the face of event that exceeds facility capacity. So that's all my presentation. Thank you for your attention.
Thank you, Dr. Minakawa, for giving a nice presentation and information about the research work carried out by your organization to protect the farmland and other areas, coastal areas from tsunami, high tsunamis. Now we request Dr. Yoshimoto to make a presentation on field surveys on recovery situation from tsunami-induced groundwater salinization in Japan.
Thank you so much. So I'm speaking on behalf of Dr. Tsuchihara. So due to some compelling tasks, Dr. Tsuchihara is unable to speak today. So, okay, just minutes. Okay. Okay. So I'm Shuhei Yoshimoto. I'm working for the researches on groundwater resources conservation. Especially, I'm working for the conservation of water resources in area with subsurface dams. So today, I will speak on this presentation titled Field Surveys on Recovery Situation from Tsunami-Induced Groundwater Salinization in Japan. This is to introduce a case of groundwater salinization induced by tsunami after the big earthquake. Okay, let's start. So that means yes. Okay. Yeah, as is known, the Great East Japan earthquake was occurred in 2011 with a magnitude of 9.0. This is the largest earthquake recorded in Japan. The tsunami caused by the earthquake resulted in huge loss of residences, farmlands, and human lives. So, due to the tsunami, 240 square kilometers of farmland were destroyed that are mainly paddy rice fields. And also, reservoirs, agricultural canals, greenhouses, and barns and livestock industry were severely damaged as well as farmlands. The left figure shows the height of the tsunami. The maximum was around 10 meters. The right figure shows the farmlands in coastal area before and after the tsunami. By this earthquake and tsunami, the northeastern Japan suffered severe structural damage. This is one of our study areas. This area, located on the eastern coast of the northeastern Japan, is one of the areas affected by the tsunami. The tsunami reached more than 5 kilometers inland from the coast. The right figure shows the tsunami flood depth of this area. The maximum was 15 meters. The yellow barrels represent the observation wells. These wells were installed by the national government. We used these wells to investigate the situation of recovery from groundwater salinization. The study area is one of the major grain producing areas of Japan. Rice is the major crop. This photo shows paddy rice fields in the study area in 2017. That was 6 years after the tsunami. The farmlands have been considerably recovered, but in some areas, the farming was not restarted at that time. In addition, the study area is known as one of the leading strawberry producing areas of the northeastern part of Japan. Many greenhouses for strawberry farming are distributed in this area. The groundwater had been used for irrigating strawberries. However, after the tsunami, the groundwater became unusable due to the groundwater salinization. Therefore, the tap water was used instead of the groundwater. Some farmers transported the groundwater from a distant big well by their own vehicles. Saltwater intrusion occurred in many of the coastal artifacts. This figure shows a schematic diagram of the typical shallow coastal groundwater system. Under the normal condition, saltwater intrusion is usually wedge-shaped. However, after the tsunami, saline water was brought inland, and then the saline water remaining on the land surface if infiltrated into the subsurface, that causes salinization of the groundwater. Okay, like this way. Yes. Then these figures show schematic diagrams of salinization of the groundwater and its recovery. Just after tsunami, the salinization was caused by infiltration of salt from the land surface. Then the farmlands were gradually recovered. A freshwater layer has been formed by infiltration of rainwater and irrigation water from the rice paddy fields through the years. In order to know the recovery situation of the groundwater from salinization, vertical profiles of electrical conductivity, that is EC of the groundwater were measured at observation wells by using this type of EC sensors. Depth of the observation wells ranges from 10 to 30 meters. The sensor probe was slowly inserted into the well, then the values for EC were recorded from shallow to deep. Here are photos of the observation wells. we periodically investigated 15 wells. This figure shows an example of EC profile of the groundwater in a well. EC measurement was done from 2017 to 2021. Interval of depth of the measurement was 1 meter. Groundwater with EC lower than 70 BGMS per meter is suitable for strawberry farming. Okay, this line, yeah. So we can see that the shallower water can be used, but the deeper cannot. However, relatively shallow part of the water was gradually recovered. Yes, this is a result of another well. This well is located inland, but a relatively large amount of salinity remained in the shallow groundwater. So it is difficult to use this groundwater for strawberry farming. Degree of recovery from the salinization, degree of recovery from salinization varies from site to site. This graph shows the annual average EC at sites A and B. The left graph is for site A. That shows EC gradually decreasing from 2017 to 2021. For this way, the salinity was reduced and the thickness of freshwater layer increased. However, as we can see the right graph, the recovery trend is not clear for site B. So it is expected to take more time for recovery. This figure shows the relationship between EC of the shallow groundwater and the distance from the coastline. This blue band indicates the range of EC available for agriculture. The freshwater layer is not necessarily thick, even if the site is far from the coast. Like this way, some of the groundwater, even inland, has considerably high EC. It can be said that remaining seawater and the recovery situation from groundwater salinization is not homogeneous. Recovery from salinization may be contributed by different factors at different proportions. Rainwater is likely the main source of fresh groundwater. In addition, irrigation water for rice paddy fields is another contributor for recharging fresh groundwater. Furthermore, groundwater flow from inland is an important factor too. Coastal areas are usually low-lying and flat, so hydraulic gradient of the groundwater is very small and the groundwater flows slowly. Due to such hydraulic conditions, it takes many years for the remaining salt water to disappear. Many farmlands were destroyed by the earthquake and tsunami, but the farmlands were gradually restored through land improvement projects by the national and local governments. As paddy rice fields were restored, use of irrigation water was gradually increased, and then groundwater recharge was also enhanced. Therefore, irrigation water has also contributed to increasing the freshwater layer. If we would like to know how the groundwater flows in an area, we investigate the residence time of the groundwater. This figure indicates the measured concentrations of sulfur hexafluoride, we call it SF6, that are corresponding to the atmospheric concentration of SF6 in the past years. As this way, we can use SF6 measurement for dating of relatively young groundwater up to 50 years. SF6 has been used for installation of transmitters or other electronic devices since 1960s, and recently the use has been largely expanded for production of information technology devices. Atmospheric concentration of SF6 in the northern hemisphere has been rising from the 1970s. Okay. If the groundwater was recharged in the past decades, the groundwater would have lower concentration of SF6 in comparison with the recent ones. This figure is the result of, this figure is the result of sampling in 2020 in the studied area. Through the comparison of SF6, the groundwater is estimated to be dated from around the 1970s to the present. Okay, this way. The highest SF6 concentration corresponds to the residence time of 70 years. The lowest does to 33 years. So the residence time of the groundwater of this area was estimated in a range of 17 to 33 years. This result shows that the flow of the groundwater is considerably slow. This figure is the result of a survey in 2020, that is 9 years after the earthquake. The red figure shows the distribution of chloride ion concentrations in the groundwater. The right is of residence time of the groundwater estimated with SF6. And the blue dotted lines show boundaries of the tsunami flood areas. The residence time tend to be large in the north. And also, chloride was relatively high in the northern area. The groundwater which flows slowly and has greater residence time is likely contain more remaining salinity. The topology of the northern part is not, the topology of the northern part is almost flat, not particularly depressed. So the reason why the saline water remains is still not clear. Further investigations are needed. Even today, saline water remains deeper in the aquifer. So in order to obtain fresh water, we need appropriate method for extraction. In one of the monitoring wells, salt water was distributed in the deeper span. If we pump the groundwater without any countermeasures, salt water moves upward. That will result in groundwater quality degradation. This upward movement of salt water in a cone-shaped manner is usually called as upconing. We need information on well depth and pumping rate that is suitable for keeping the water quality acceptable. So, yeah, for this purpose, pumping tests at multiple depths at each site are necessary. However, the test, the test require the installation of many survey wells, which cost so much. Therefore, it is not practical. So we have applied the sampling method using a pumping packer system. pneumatic packer was installed at the boundary between freshwater and salt water, and then the groundwater above the packer was pumped. Using this freshwater saltwater partition, we can carry out pumping tests at any depth in a single well. Namely, well with a packer installed can be considered as a shallow well. So we can monitor if the pumped water is suitable for agriculture by using EC sensors. So if we plan to dig new wells, this type of the pumping test enables us to determine adequate pumping depth and pumping rate. The left photo is the pumping device with a packer system. The device number 1 is the packer. The packer is made with rubber. Handy air pump is used to inflate the packer. The device showing the left is an electric pump. The power source is a car battery. The regulator for pumping flow rate is now number 6. The pumping test starts with inserting the packer and the pump tube into the well, and then the packer is inflated by the air injection using the handy pump. So for this well, by adjusting pumping rate into around 10 to 15 liters per minute, seawater ponding was adequately prevented this way. Yeah, prevented this way. This is a whole view of the in-situ pumping test using the packer system. Here is the well, and this is the equipment. The left figure shows the distribution of EC in the groundwater pumped without packer. The right is down in the pumped groundwater at the optimum depth using the packer. In the blue areas, we can obtain the groundwater suitable for strawberry farming. The blue number indicates the optimum packer depth. If the pumping depth is too shallow, the groundwater level will rapidly decline, and then pumping may be stopped. Therefore, it is important to find the appropriate depth for pumping without upcoding. Yeah, this is the summary of this presentation. Okay, so thank you so much for your attention.
Thank you, Dr. Yoshimoto, for giving a very informative and nice presentation on how the groundwater salinization happened due to tsunami, and then what measures were taken to extract the fresh water from the salt-affected groundwater aquifers. So now we invite Dr. Katoshi Shirahata to make presentation on a study on aquifer hydraulic properties using tidal response method for groundwater resource development. Dr. Katoshi.
Thank you. Can you hear me?
Yeah, we can hear you.
I will start. My topic, from a little different point of view, I present a method that utilizes tidal waves, not protecting something from tidal waves. I present a simple method to know hydraulic properties of coastal aquifer using tidal response of groundwater level. In the first, a little long part of the presentation, I explain the background. When we are going to develop groundwater resources in a regional scale, we need aquifer hydraulic parameters such as hydraulic conductivities. To estimate aquifer hydraulic parameters, pumping test is a widely used method. However, it is sometimes difficult to use for a coastal aquifer because the pumping may cause uprising of the salt water underlying the fresh water and deteriorate the freshwater resource. And also, groundwater level in coastal aquifer often shows periodic fluctuations affected by tides in adjacent surface water, such as ocean. We say this tidal response of groundwater level. Because the pumping test is a method analyzing the groundwater level decline caused by the pumping, these natural tidal fluctuations make errors in pumping test data analysis. On the other hand, the tidal response of groundwater level in coastal aquifer has been used for investigating aquifer hydraulic properties because the response itself is related to aquifer parameters. The upper panel demonstrates confined aquifer and the lower panel demonstrates unconfined aquifer. In both cases, the groundwater tidal fluctuations propagate inland from the boundary with the tidal surface water with a decrease in amplitude. The describing formula for the ideal simplified case is this. When the adjacent surface water oscillates sinusoidally with an amplitude of H0 and period P, the groundwater level in aquifer at a distance x from the boundary shows oscillations with an exponentially attenuated amplitude and linearly lagged phase. The attenuation and the lag are related to aquifer hydraulic parameters. Here it is shown by D. This is hydraulic diffusivity. By transforming this formula, we can derive this formula for calculating hydraulic diffusivity. The directly calculated parameter is hydraulic diffusivity, but this can be transformed into hydraulic conductivity if some other parameters are known or assumed. With that background, we developed a new tidal response method. We improved conventional tidal response method by 2 points. First, in our tidal response method, we disused surface water fluctuation and used groundwater fluctuation at 2 sites, near shore and relatively inland. By this, we can offset undesired effect of the sloping boundary of the ocean and aquifer. Second, in our method, we extract tidal sinusoidal oscillations with one specified period from time series data. This can be implemented using normal spreadsheet software with its built-in functions following the Fourier series expansion formula. In summary, we have a simple, accurate tidal response method that uses only generally available autologging devices and spreadsheet software. In the following, I present application to an island aquifer. The study island is Tarama Island, one of the Ryukyu Islands, southwestern part of Japan. From there, the surface of Tarama Island looks like a patchwork of brown and green squares. Brown part is mostly the field of sugarcane before growing tall, and green part is mostly the field of tall sugarcane or meadow. As you can see, agriculture is the principal industry in this island. The surface geology of Tsunami Island is dominated by highly permeable limestone, and rivers do not exist in the island. Groundwater is the principal water resource in the island. It provides the source of domestic water supply for a population of about 1,200. The local branch of the National Administrative Office in charge of this area is starting water resources development, including groundwater development for agricultural use. They desire simple and inexpensive method to estimate aquifer hydraulic parameters in order to make a numerical groundwater model. So the developed hydro response method was applied. Observations were made using submersible water level loggers deployed in groundwater observation holes near shore and relatively inland. This black circle and blue one. We collected a pair of groundwater level time series data from the near shore and inland sites in the island. The length of the analyzed data was so set as to provide accurate Fourier analysis outputs. Outputs are amplitude and initial phase of the sinusoidal tidal components. The Fourier analysis calculation can be completed copying the observation data to an Excel sheet with pre-entered formulas, and we can get amplitude and initial phase of the tidal component. And if we input the propagation distance, we can derive hydraulic diffusivity. And further, if we input the storage coefficient and aquifer thickness, we can derive aquifer hydraulic conductivity. This is the result of the application. In this application, one representative nearshore observation site was paired with each of 4 inland sites. This assumes that the groundwater level fluctuations along the surrounding coastline is identical to those observed at the nearshore site. Hydraulic diffusivities were calculated for aquifers beneath these shown 4 investigation lines. The diffusivities can be transformed into hydraulic conductivities. The aquifer hydraulic conductivities obtained from the tidal response method are used by the administrative office in making a numerical groundwater model that require information on the conductivity distribution. This is the last summary. We developed a tidal response method, accurate but simple. It is practicable only using normal ground level observation devices and spreadsheet software. The method facilitated the investigations on hydraulic properties of kilometer-long coastal aquifers. That's all. Thank you.
Thank you, Dr. Asashi, for giving a very enlightening presentation on the research carried out on groundwater development in the tidal response area, and to measure how to measure the tidal response in terms of amplitude and oscillations, and then hydraulic conductivity of the groundwater. So now, with this, all the presentations are over. We can go for question and answer. So there are some questions which are already posed by the participants. They are in the Q&A question and answer box. So we request respective speakers to go through the question and then respond And any attendee, any participants who wants to raise a question, so they can also raise hand, and then depending on the availability of time, we may provide them some of them a chance to raise the question and interact with the authors or speakers. किसका question है? Question पढ़ दो.
Tariq Ibrahim.
बताओ.
Tariq Ibrahim Jain.
रेज किया क्या? रेज किया?
Raise.
नहीं, वो तो क्वेश्चन पढ़
Yeah,
दो.
now it is. Yeah, he is. Mr. Tariq, you have given access to speak. You can speak now.
Okay, thank you very much. Thank you. My question, this is Tariq Ibrahim from Pakistan Meteorological Department. My question was from Dr. Hariko regarding water block breakwater block. Is it work? As he mentioned in his presentation that wave height of 2011 tsunami is greater than 14 meters. So at that point, series of waves and the blocks, they can prevent or reduce the intensity of wave height. Thank you. I hope I have conveyed my question.
Please. Dr. Minakawa, if the question is meant for you, you can respond to this question.
Thank you for your question for me. So in your question, so it means breakwater block means coastal dike or not? Block?
So sorry, I couldn't get your point, doctor.
So in your question, so you mentioned about breakwater block technique, right? So is it the technique for
Yes.
coastal dike?
Yeah,
What-
dike and yes, dike and blocks or etc. you are using.
But today's presentation is not my research, so I'm not sure. But so we have some technique to construct tenacious dikes by using some tools. But so sorry, so I'm not sure. But so maybe if the dike can maybe have an effect for big waves. But sorry, I'm not sure now.
Okay, thank you, doctor. Thank you very much.
Yeah, President Professor Raghav, you have raised the hand, you can raise your queries.
Yeah, thank you, Harish. It's related to if well, any of the speakers can give an indication whether they are willing to adopt a salt-tolerant crops, non-conventional crops, that they can tolerate that high salinity. For example, that sugar beet barley, maybe another type of salt-tolerant rice. For grazing areas, there are some type of grass they can tolerate high salinity, like Bermuda grass. Some other non-conventional cereals like quinoa, amaranth. So there are type of crops and grass they can tolerate more high salinity. And I wonder whether my Japanese colleagues are having this in mind to change the crop pattern to non-conventional type of crops that they are salt tolerant. I would be grateful if they can shed some light on this. Thank you.
Thank you so much. I'm Shuhei Yoshimoto. Yeah, actually, in Japan after the earthquake, so I'm not sure some not conventional crops such as the sugar sugar beet, or yeah, as my understanding, many of the farmers in Japan, they want to profit. They want to cultivate profitable crops such as strawberry or some good quality of rices. So actually, that is my thought, but they didn't think of some alternative crops for the salinity. So probably, so yeah, the such crops alternate. I understand such crops alternative measures for the some areas, but I think that is case by case. Is it okay? My answer is okay.
Yeah, thank you, for Dr. Minakawa for giving that response to the query raised by our president. Now we request President Order Dr. Warshus. He has some query and he has raised some question in the question answer session section. Dr. Schultz.
Thank you, Harish, very much, and thank you for the presentations. Very interesting. My question that I put on the question item is: I understand that the presentation of Dr. Minakawa was mainly based on the report of NARO, and if possible, I would very much appreciate it if I could get a PDF of that report. I suppose it is in Japanese, but I think Google Translate can assist me. I'm especially interested in the work that was done on the land use zoning, as well as on the safety standard, because there are not many countries that have a safety standard of 1 in 1,000 years, which is, I fully understand that the Japanese have raised the standard to that level. But the interesting point there also is for me that this 1 in 10,000 is a combination of measures that they apply. And I don't know about another example where that combination is being applied. So I would be very much interested if I could get a copy of that report. Thank you very much.
Thank you, Dr. Schultz. So maybe it's possible to send PDF for you, but it's just in Japanese, so
yeah, I understand.
it's needed. But I asked to my boss. Maybe it's possible. Yes.
Okay, thank you very much.
You.
Professor Kao, you have raised the hand. You can now raise your queries or questions or suggestions, whatever they are.
Yes, thank you for very good presentation. I have a comment to the Dr. Minakawa, because for your rebuilding of the sea dike, your return periods will be from the 100 years and to the 1,000 years. I think it will be the very big and very huge of the sea dike, just like a very hard of walls. It will limit the people approach the coastal area. But do you have any idea try to solve this problem from the offshore? Just like from offshore, we can dispersion of the tsunami energy or something, some surge, just like growing or anyway. Do you have any idea?
So now, so I have no idea, because so today's presentation, I learned the result of our colleague research. So if you send a question for me, so I talk about your question with my colleague. So sorry, I'm not sure now.
Yes, in normally, as I know, the Japanese governments have many coastal engineer research and some of the facilities in the some of the how to say transportation ministries. They have many carry out many physical modeling and about the some decades the engineer of the coastal engineering or scholar, they have some suggestion to the Taiwan. They offshore structure can be dispersion of the energy from the typhoon wave, but now we can simulate using the tsunami. I think I have given you this comment. And the other questions for the what the gentleman Shirahata, right? You using the groundwater modeling to analysis of the conductivity of groundwater concentration, and the water level is affected by the tidal variation. I think it's quite difficult to analyze, but I see you using the fast Fourier series transform to analysis this. I think is available, but how to calibrate? Just only using the fire investigation data, and do you have any any others how to I don't know. Do you have any idea to developing the new method of the groundwater level?
Please make the report available for ICID.
Thank you.
Well, thank you, Dr. Kao, for raising your queries, and then to all the speakers, panelists who have responded to the questions. Now we don't have any more questions and raise hand. So, and then time is also coming to close. So we'll close this webinar. And before that, we request Vice President Dr. Mohammad Ghazli. And for concluding remarks, we request our President, Professor Raghav, to give concluding remarks and close the webinar.
Thank you very much, Harish. And yeah, it's excellent presentations today. And also we have seen new technologies coming to our help, especially for how to cope actually with the tsunami impact from the engineering side and also from an instrumental side. So it is really quite a good input today to our knowledge. And I thank all the speakers, and I thank also the chair of the working group for getting this virtual meeting and that excellent webinar today. And I thank you all, and until we see each other again in the next webinar, thank you very much.
Thank you, President Professor Raghav, for giving your concluding remarks. And for information of all the participants, recording of this webinar will be available on our website in a day or two after we process it properly, and it will be available. And we'll also try to get presentations and permissions from the authors. If they are agreeable, then we'll also put the presentations on the webinar of this presentation of this webinar on our website. So thank you very much.
And if you can get the report also available for everyone, that would be great.
Yeah, that if first Dr. Minakawa will find out from his office whether the report can be shared.
Yeah.
And then since the report is in Japanese, so if any individual, they may contact Dr. Minakawa for a report.
Yeah.
And then if it is shareable, then if it is shared with ICID central office, then we'll also put it on the website.
Shall we take a photo now?
Yeah, may I request everyone to, yeah,
Attendees को तो आएगा नहीं photo. Take photo.
Is the central office taking a photo?
Yeah, we'll take the photo, but photo will be only of panelists. It will not be of attendees.
thank you, sir.
Thank you. Thank you all the participants for sparing
you.
your time to attend this webinar, very useful webinar. And thank you. Bye, everybody.
Goodbye.